Imagine an AI, as powerful as the ones humming away in these huge data centers, crunching data like crazy. But imagine it running right there on your smartphone, using hardly any energy, always there, even if you're offline. Sounds like science fiction, right? Well, what if I told you that maybe that future is a lot closer than we think, and is driven by something kind of counterintuitive? Today, we're diving deep into a breakthrough that could actually make this happen, the really fascinating world of one-bit large language models. And specifically, we're looking at this incredible BitNet B1.58 architecture. For years, the thinking for powerful AI was basically bigger is better, more precision, more power. But what BitNet B1.58 seems to be showing us, and we'll unpack today, is maybe a whole new scaling idea. One where the path to truly widespread, powerful AI might actually be found in sacrificing some of that precision for just massive, super efficient scale.
That's precisely right. For a long time, yeah, the main way to get more powerful AI was just this relentless chase of bigger is better, pushing model sizes, parameter counts, the computational needs, just up to staggering levels. But this approach is hitting some really serious walls. Walls of cost, energy, accessibility, just unavoidable hurdles. We'll dig into what we call the scaling dilemma and how these one-bit LLMs offer a pretty radical new way forward. It's fundamentally redefining what's even possible.
Okay, so our mission for you today is to unpack the technical wizardry behind these models, understand why they're so incredibly efficient, and how they still manage to perform so remarkably well. I mean, sometimes even better than bigger, full precision models on certain tasks. That's wild. And what this all means for the future of AI, from the phone in your pocket to global sustainability. We're talking about a real paradigm shift here.
Yeah, and to bring you these critical insights, we've really taken a deep dive into the technical reports, the latest research papers, detailed analyses. We're focusing quite a bit on Microsoft Research's pivotal work on BitNet B1.58 naturally. We've tried to synthesize the most important stuff, the key nuggets of knowledge, and the latest empirical evidence to really shed some light on this groundbreaking field for you.
Okay, let's pull back the curtain a bit on where things stand with advanced AI right now. When we talk about models like OpenAI's GPT-3, 175 billion parameters, or even the newer, massive ones, they've totally blown us away, right? Their capabilities are amazing, generating text, translating languages, even tackling complex reasoning.
Okay.
But that wow factor, well, comes with a very real, very heavy price tag, as you might expect.
Indeed, it does. This exponential growth in model size isn't just some academic thing. It translates directly into huge practical challenges. These models are pretty much stuck using high-end specialized hardware, mostly powerful GPUs like NVIDIA's A100s or H100s, stuff that costs tens of thousands of dollars each. And that hardware, it's usually packed into these massive centralized data centers. Just to give you a concrete idea, if you wanted to load even a, let's say, moderately sized 13 billion parameter Llama model, you'd need about 26 gigabytes of memory just for the parameters, assuming standard 16-bit format.
26 gigs, just for the model weights.
That's the weights. That's more dedicated RAM than a lot of high-end gaming PCs have, let alone your average laptop.
That's a staggering figure. And what really concerns me is what this scale means for, everyone else. These billions of parameters aren't just numbers, they're a huge barrier. If you're an independent researcher or a small startup or even a medium-sized company, getting access to these cutting-edge tools or trying to replicate them, you're almost totally reliant on just a handful of giant organizations with massive resources. It basically centralizes AI innovation and power into, very few hands. That can definitely stifle broader development and limit the kinds of applications we see.
And that centralization, yeah, it has a direct impact on the financial and environmental burden these models carry. The money side isn't just for big tech. Training these things from scratch, we're talking tens, maybe hundreds of millions of dollars. Even just running the models, inference, getting responses, the operational costs add up quickly. It creates this massive barrier to entry for smaller businesses, individual developers, academics. Makes it incredibly hard for them to innovate or even access these tools without relying heavily on cloud providers.
And then there's the environmental cost, which people are rightly starting to talk about more and more. These intensive computations, they contribute significantly to global carbon emissions. It's a real issue. I've seen estimates suggesting training one large LLM can use as much energy as hundreds of homes for a year, or even rival the carbon footprint of making and driving a small car over its lifetime. If we just keep going down this path of bigger and bigger models, more energy use, it's just fundamentally unsustainable. economically and ecologically. It's a critical bottleneck, frankly. We can't just keep ignoring it.
What's fascinating here and kind of worrying is that this isn't just, an inconvenience for the tech giants. It's a critical bottleneck that really threatens to limit AI's full potential. It's accessibility, it's democratization for everyone. If we keep going like this without some radical change, advanced AI stays a luxury, right? Stuck in expensive data centers. It won't become that universally available utility we maybe hoped for. And that really restricts who can build with AI and who benefits.
Okay, so if the usual path, the bigger is better path, is leading us straight into this wall, prohibitive costs, unsustainable resources, the obvious question is, how do we get around it? How do we make AI powerful and practical without needing a supercomputer everywhere, without this huge carbon footprint? And this is where the ingenuity of model compression really comes into the picture. #, model compression and the power of quantization.
Right. This huge challenge has, well, unsurprisingly, sparked a ton of research into something called model compression. If you follow AI, you've probably heard of things like pruning. That's where you try to remove unimportant connections in the network, or knowledge distillation, where a smaller student model learns to copy a bigger teacher model. There's also low-rank factorization, which simplifies the big, complex matrices inside. The core idea behind all of these is basically shrink the model, make it less complex computationally, but try really hard not to hurt its performance too much.
So for a while, it's been like trying to find a really good way to compress the model's intelligence, like a JPEG for AI. Some techniques looked at the structure, others at the behavior. And these have all been super important tools, definitely bought us some time. But with LLMs getting into the hundreds of billions of parameters, the game totally changed. We needed something, well, more radical.
Exactly. Those techniques have been essential, yeah, but one method has really emerged as like a central, maybe even groundbreaking strategy for LLM optimization, mainly because of its direct and profound impact on memory, energy, and speed. And that's quantization. This isn't just about making models smaller. It's about fundamentally changing how they represent numbers, how they process numbers, right down at the core. And that's where things get really, really interesting. That's where the paradigm shift really starts.
Okay, let's dive into that. So most traditional AI models, since forever basically, have used 32-bit floating point numbers for their parameters. Think of it like having millions of colors for every pixel in a super high-res photo, capturing every tiny shade. Quantization basically asks, do we really need all that insane precision for every single calculation? Or can we, cleverly reduce the number of colors without losing the main picture? It's about taking those high precision numbers, like FP32, and mapping them to lower precision formats, like FP16 or 8-bit integers, INT8, or even 4-bit, INT4.
Precisely. And by going from, say, 32-bit floats down to 8-bit integers, you're cutting the memory needed for each parameter by 3/4. That's a massive saving. It doesn't just shrink the memory footprint, which lets the model fit onto smaller hardware. It also significantly cuts energy use and speeds up the math. Because, well, operations on simpler, lower precision integers are just inherently faster and less power hungry for the chip. It's like swapping a massive multi-volume encyclopedia for a really concise, but still incredibly effective pocket guide that gives you all the crucial stuff.
And these efficiency gains are huge, right? They make models way more nimble, much cheaper to run, much more practical for loads of applications, especially on edge devices. But here's where it gets truly revolutionary. Moving to 4-bit was already a big deal. But 1-bit LLMs, that's like a quantum leap. It's not just tweaking the engine. It's like inventing a completely new propulsion system, like going from a bicycle to a jetpack, efficiency-wise. It's a fundamental rethink of the computational core itself, pushing the boundaries of what we thought was even possible.
Exactly. Projects like Microsoft's BitNet B1.58 are really kicking off a new era. They're showing you can get performance that's comparable to, and sometimes even better than, full precision models, but with orders of magnitude, less memory, much lower latency, and dramatically less energy use. This fundamentally just breaks the old cost-performance curve for LLMs. Think about this. A model with 1 billion parameters. In standard 32-bit floats, that's 4 gigabytes of memory. That same model, in a 1-bit format, only 125 megabytes.
125 megs instead of 4 gigs.
That's a 32 times reduction. It's absolutely staggering.
And connecting this back to the bigger picture, this isn't just about slightly faster chatbots or saving big tech some money. This looks like a potential, maybe even radical, solution to that scaling crisis we talked about. It could pave the way for a more sustainable, more accessible, and ultimately more democratic future for AI. where these powerful tools aren't just locked away in giant data centers. It really changes the whole landscape.
But yeah, this raises a really profound and critical question. How does something with so little information per weight, just 1 bit, or maybe a tiny bit more, still manage to be so smart? How do you possibly keep that competitive accuracy when you're being so incredibly aggressive with the compression? And this is where understanding the theoretical underpinnings and the really ingenious training methods becomes absolutely crucial. Let's get into that. Hashtag theoretical foundations of 1-bit LLMs. Okay, so at its heart, quantization is about taking something continuous, like any real number in a range, and forcing it into a small, fixed set of discrete values. Every time you cut the bit width for your parameters or activations, you're making this fundamental trade-off. You get amazing efficiency, like that 32x memory reduction we mentioned, but you also inevitably introduce some amount of noise or quantization error. That error is just the difference between the original high precision value and its new lower precision version. The whole art, the central challenge really in quantization research is managing that noise, minimizing it so the model still gets the patterns right, still understands the data, keeps its intelligence.
So it's not just about randomly chopping bits. It's like trying to draw a really detailed architectural plan, but with only like 3 colors and maybe 2 line thicknesses. You have to be super smart, super strategic about how you simplify it so you still convey all the essential information, the structure, without losing the whole building design. This balancing act seems absolutely crucial for why these models even work. It's about doing it smartly.
Precisely. And this is where the method you use for quantization becomes just as critical, maybe even more critical, than the final bit width you're aiming for. To really get why 1-bit LLMs perform so well, we absolutely have to understand the key difference between 2 main approaches: post-training quantization, or PTQ, and quantization-aware training, or QAT. This difference, it's foundational to why BitNet B1.58 works so well.
Okay, what's the core difference there? And why is one so much better for this kind of extreme compression?
Right, so PDQ is the simpler way, the more intuitive one maybe. You take a model that's already fully trained in high precision, say 32-bit floating point, your masterpiece, and then after training is done, you convert its weights to the lower precision format. It's convenient, sure, because you don't have to retrain the whole thing, but this often leads to pretty severe performance drops, especially when you go to really low bit widths like 4-bit or especially 1-bit. The model learned all its complex patterns in this rich, high-precision world, right? And then you suddenly yank away all that detail after it's learned. It can cause what some researchers genuinely call brain damage.
Brain damage, okay.
It's like teaching a concert pianist perfectly and then telling them they have to perform wearing thick mittens. The results aren't going to be pretty.
Right. So PTQ is like mastering a skill with all the best tools, then suddenly having half of them taken away right before the big show. Your mastery depended on those tools, so you're going to struggle. Makes sense.
Exactly. But QAT. QAT is fundamentally different. With quantization-aware training, the effects of quantization are simulated during the training process itself, right from the start. The model is forced to learn how to do its job under these low-precision constraints from day one. It's not an afterthought. It's baked right into the learning. By simulating that quantization error and feeding it back into the training objective, the model's optimizer learns to adjust the weights not just to get the task right, but also to be explicitly resilient to the noise that quantization introduces. And this is the absolute key reason why high-performing 1-bit LLMs like BitNet B1.58 are even possible, why they avoid that brain damage. The model learns internal representations that are just inherently robust to low-precision math.
Wow. Okay, so that's a massive insight. It's not just what you quantize, but really when and how you do it. QAT changes the whole learning game, letting the model adapt and even thrive in that low-precision world from the get-go.
And that brings us right to defining what 1-bit actually means here. Because it's not always just a simple binary on or off. The term 1-bit LLM is kind of a broad umbrella for models using extremely low bit width weights. The purest form, yeah, is binary. Each weight is just one of 2 values, like notch 1, +1, or maybe 0, 1. That gives you the absolute maximum compression.
Right, so when we hear 1 bit, it's not always just strictly on or off. These BitNet B1.58 models, they're actually using a clever trick with 3 values, aren't they?
Yes, precisely. BitNet B1.58 uses a ternary representation. Each weight can be one of 3 distinct values, notch 1, 0, +1. And this ternary system is often called 1.58-bit. That number isn't random, it comes from information theory. The number of bits you need to represent n possible states is log base 2 of n. So log base 2 of 3 is about 1.58 bits, and including that 0 value, that neutral state, it turns out to be a really critical improvement over just pure binary. It adds a surprising amount of expressive power for very little extra cost.
That E0 must be a huge deal then. It kind of feels counterintuitive, adding a third state when you want ultra-low precision.
It's an enormous deal. Think of it like a neural switch, but with an explicit off position. The +1 and -1 values, they let the model boost or suppress a signal, right? Positive or negative correlation. But the 0 lets the model explicitly say, nope, this connection, this specific piece of info, irrelevant right now, turn it off.
Okay.
This ability to do explicit feature filtering, to dynamically prune connections on the fly, it's a form of learned sparsity, and it massively enhances the model's expressive power, its ability to manage information flow. It makes the network smarter, more focused. It leads directly to better task performance compared to just plain binary models.
Wow. Okay, so this clever ternary system is really foundational to BitNet's performance. It lets it ditch unnecessary information and focus its limited resources where they actually matter. But understanding that it works is one thing. Seeing how it's actually put together inside a transformer model, like at the layer level, that really shows the engineering brilliance. Let's dig into that architecture.
What's really cool here is that the BitNet B1.58 architecture is just incredibly pragmatic engineering. It's not about just blindly slapping extreme quantization everywhere and hoping it works out. Instead, it very strategically targets the absolute most computationally expensive parts of the transformer, while carefully keeping precision where it's really critical for stability and performance. It's a very targeted strike for efficiency.
So the heart of this must be some kind of special building block that handles this weird ternary math.
Exactly. The core innovation, the real engine driving this efficiency, is called the bitlinear layer. This is a custom design module, and it's designed to be a direct drop-in replacement for the standard linear layers you find everywhere in transformers, like torch.nn.linear if you're using PyTorch. And here's why that's so important. The main computational bottleneck in any big language model, the thing that takes up almost all the calculation time, is matrix multiplication. Especially within the self-attention mechanism and those feed-forward network layers. In normal LLMs, this means multiplying huge matrices full of high-precision floating-point numbers, which is incredibly time-consuming and uses a ton of energy.
And the bitlinear layer just sidesteps all that heavy floating point math. It fundamentally changes how those core calculations are done.
Totally. By forcing the weights into that simple ternary set -1, 0, +1, the bitlinear layer completely gets rid of the need for complex floating point multiplications. Instead, that big matrix multiplication turns into a series of much simpler, much faster integer operations, basically just additions, subtractions, or sign flips, and setting things to 0. This fundamental shift from multiplication to mainly addition-based math is the primary reason we see these dramatic drops in latency, energy use, and memory bandwidth needs in BitNet models. From a hardware perspective, these are operations that a processor's ALU, arithmetic logic unit, can do way, way faster and using less power than firing up the complex floating point units.
That's really clever. So those three values, many of 1 + 1, they aren't just random picks. They each have a specific super cheap job inside that bitlinear layer.
Absolutely. Multiply an activation by +1. That's just an identity operation. The value passes through unchanged. Trivial. Multiply by -1. That's just the sign flip. Again, super easy in binary math. But like we said, the real game changer is multiplying by 0. That operation just nullifies the activation completely, stops it from propagating forward. This ability for explicit feature filtering lets the model learn which inputs are just irrelevant for a particular calculation and effectively prune those connections dynamically on the fly. It acts as this powerful form of learned sparsity. It massively boosts the model's expressive power, helps it manage information flow better, leads directly to improved performance overall. It's a really elegant way to keep the model focused.
This learned sparsity, thanks to that 0, clearly gives BitNet B1.58 a big advantage over just plain binary models. It's a really smart use of a simple value to make the model smarter.
It really is. Now, during training, obviously, the model can't just work with these discrete -1, 0, +1 values for doing gradient calculations, because gradients need continuous values. So it keeps a full precision shadow copy of its weights running alongside. These are continuous floating point numbers. Then, for the forward pass of every training step, these high precision weights get dynamically quantized on the fly using a specific method called abs mean quantization. This involves two main steps. First, the weight matrix gets scaled by its average absolute value that normalizes things. Then, the scaled matrix gets rounded to the nearest integer and then squashed basically, to make sure all values land exactly in our target range of -1, 1. So they snap neatly to -1, 0, plus 1. This makes sure that every single computation uses those incredibly efficient ternary weights.
Okay, so it's like having this highly detailed master blueprint for a building that's the high-precision shadow weights, which is constantly being tweaked and refined. But when the actual construction crew is on site, they only use a simplified, really clear, step-by-step daily work plan that's the dynamically quantized ternary weights for the actual heavy lifting.
Fantastic analogy. Yeah, the abs-mean function is exactly that work plan creator. It normalizes the weights, then snaps them to -1, 0, plus 1. This guarantees that those computationally heavy matrix multiplications always use the ultra-efficient ternary weights, massively cutting the computational load.
This sounds incredibly aggressive on the weights, though, so it
It-
can't be all 1.58 bits everywhere in the model, can it?
Yeah.
There must be some kind of clever mix, right? Keeping some parts at higher precision to keep information flowing properly.
You're absolutely right. This is a really critical part of the BitNet B1.58 design, and it shows that pragmatic engineering again. While the weights are indeed super aggressively quantized to 1.58 bits, the activations, that's the data flowing between the layers, they're quantized to a more moderate 8-bit integer format. This scheme, they call it W1.58A8, weights 1.58-bit, activations 8-bit, is a really crucial compromise. You get the vast majority of the efficiency gains from the quantized weights because that's where most of the parameters are. But you keep enough detail, enough fidelity in the activation data stream to stop significant information loss and maintain strong performance. And furthermore, the BitNet B1.58 architecture very wisely adopted several stable, robust components from already successful modern transformer models like the Llama family. This is just smart engineering, right? Leverage stuff that's known to work well while you innovate on the core computation. So this includes things like root mean square normalization, RMS norm, and a variant called sub-LN. Both are used to stabilize the network during training and inference. And interestingly, they removed the specific bias terms usually found in these layers.
Why remove the biases?
That's a subtle but pretty critical choice for these extremely quantized networks. Sometimes those bias terms can introduce numerical instabilities that get kind of amplified in a low precision environment. Removing them helps keep things stable.
Gotcha. And what about the activation functions, the things that decide neuron outputs?
Yeah, for the nonlinear activation functions, they use modern, efficient choices like SWIGLU. Interestingly, the specific open source 2B4T variant of BitNet B1.58 uses something called squared RU-LU, or ReLU, in its feed-forward layers. That's not random either. ReLU is known to actually encourage more sparsity in the activations themselves, which perfectly complements the learned sparsity we get from the ternary weights. Basically, it helps the network switch off even more irrelevant information flow, boosting efficiency even further. And for positional information knowing word order, which is crucial, they use rotary position embeddings, or ROPE. That's a highly effective, widely used technique now.
And keeping that final output layer in higher precision. Yeah, that makes total sense. You spend all this effort doing efficient processing. You don't want the final answer to suddenly turn into garbage. It's the very last step.
Precisely. That final layer, the language model head, or ILM head, its job is to take the model's final internal state and project it into probabilities over the entire vocabulary, thousands of possible words. This layer is super sensitive to numerical precision. Even tiny errors here can really mess up the likelihood of picking the right next word. So keeping this layer at full precision, usually 16-bit floating point, FP16, ensures you get stable, accurate probability distributions for generating text. That's absolutely crucial for getting coherent, reliable, high-quality output.
Okay, this careful balancing act, aggressive quantization for weights, strategic precision for activations, and the critical output layer, it's clearly key. But how on earth do you even train a model to work so well in this low-bit world? It sounds incredibly tricky, given how discrete those weights are. #tag training methodologies for natively quantized models.
That's an excellent question, and it really gets to the heart of why BitNet B1.58 is so successful and why Q8T is such a leap forward. The ability of these 1-bit LLMs to keep performing so well isn't just because of the clever architecture. It's deeply tied to the specialized training methods used to build them. The training relies on the sophisticated dual representation strategy. It elegantly solves that fundamental problem.
Yeah.
How do you use continuous gradient-based learning when your weights are discrete?
Right, this is where the quantization-aware training really comes in. Is the model isn't just told be 1 bit afterwards. It learns to compute as if it's 1 bit right from the start, building its intelligence around those constraints.
Exactly. The core idea is inserting these fake quantization operations directly into the model's computational graph during training. These operations basically mimic the effect of low-precision math during the forward pass. So for each weight matrix, the model does that scaling and rounding to get a ternary version, just like it would during actual use inference. And that quantized version is then used for the calculations that follow. By doing this, the model is forced constantly to learn and adapt while dealing with the information loss and numerical noise that comes with quantization.
So it's like constantly practicing in its low-precision environment. Like maybe a musician learning to compose brilliant music using only a very limited set of notes. It forces incredible creativity and efficiency with what they have. That must build amazing resilience into the model.
Precisely. The quantization error that results from this process gets implicitly factored into the final loss calculation. So when the optimizer does its job, using backpropagation to minimize that loss, it has to find a set of parameters that not only work well for the task itself,
Yeah.
but are also inherently robust to the effects of being quantized. This process effectively teaches the model to operate optimally in that low-bit world right from the beginning of training instead of trying to clumsily adapt afterwards.
But this still sounds like a massive technical headache. How do you teach a machine to learn when part of its core process, like that rounding step, snapping a continuous value to one of just 3 discrete states, how do you deal with that when its mathematical derivative is basically 0 everywhere? How do gradients even flow back to update anything?
Ah, yes. This is where one of the most clever tricks in deep learning comes in. It's called the straight-through estimator, or STE. The problem you point out is real. That rounding operation in quantization is inherently non-differentiable. If the gradient for an operation is 0, no learning signal can flow back through it. Training just stops dead for that part of the network. So the STE is this ingenious workaround. It provides a usable, though technically approximate gradient. Here's how it works. During the forward pass, the model uses the normal rounding function to quantize its weights. Fine. But during the backward pass, when calculating gradients, the STE just swaps out the true and problematic derivative of the rounding function and replaces it with the derivative of the identity function, which is just 1.
Whoa. Okay, so it's basically pretending. It's saying, look, for the sake of learning, let's just assume this rounding step was perfectly smooth and differentiable and let the learning signal flow back as if nothing happened. It's like building a little detour around a mathematical roadblock.
Exactly. It lets those continuous gradients pass straight through the discrete, non-differentiable quantization steps as if they weren't even there. This allows us to use standard gradient-based optimizers like Atom or SGD to actually train the model effectively, end-to-end, which would be almost impossible otherwise. Without SDE, trying to train high-performing one-bit models using standard deep learning techniques would be practically impossible. The training would just grind to a halt.
Okay, so even with STE letting gradients flow, you're still applying these continuous gradient updates to weights that are fundamentally discrete for the actual computations.
Yeah.
How does that work? You mentioned a dual representation. Are there like 2 versions of the weights living side by side during training, one for doing the math and one for learning?
Precisely. That's exactly what we call the dual world approach, and it's absolutely foundational to QAT. To manage applying continuous gradient updates to these inherently discrete weights, QAT frameworks maintain full precision shadow weights throughout the entire training process. Think of these high precision shadow weights as like the architect's master plan. They are continuous floating point values, and they're constantly being refined with subtle, precise adjustments based on the learning signal coming back via the gradients. Then, for the forward pass of each training step, these high-precision shadow weights get quantized on the fly into their ternary representation, tau of 1 is 0 plus 1, using that abs mean function we talked about earlier. These temporary quantized weights are then used to do the actual computationally efficient matrix multiplications. After the forward pass, the model's loss is calculated, and gradients are computed via backpropagation, using STE to get through those tricky quantization steps.
And crucially, the continuous gradients are applied to update the master plan, the high-precision shadow weights, not the temporary quantized work plan used for the computation.
Exactly. The calculated gradients, which are continuous, high-precision values, are then used to update the high-precision shadow weights, not the temporary quantized ones. This ensures the learning process is stable and precise over potentially millions of training steps. It stops the training from becoming unstable or getting stuck because of the discreteness of the weights used in computation. This dual-world approach really combines the best of both. You get ultra-low precision computation for efficiency during the forward pass, and you get high-precision optimization for stable and effective learning. This is the algorithmic secret sauce that makes these high-performing 1-bit LLMs a reality. It lets them learn effectively without losing their low-bit identity. Then, once training is all done, you just discard the high-precision shadow weights, and you save only the final, super-efficient, quantized model for actual use.
That's an incredibly intricate but really elegant process. The specific open source model we've been talking about, the BitNet B1.58 2B4T model, it went through a pretty rigorous multi-stage training using these principles, right? It sounds like a very deliberate step-by-step education.
It is, absolutely. Training such a sophisticated low-bit model isn't just one step. It's a carefully planned, multi-stage journey. The first phase was huge. Large-scale pre-training from scratch on a massive dataset, 4 trillion tokens of public text and code. This initial stage is all about the model just absorbing vast amounts of general knowledge, learning language patterns, understanding the world from data. They started with a high learning rate to grasp the big picture quickly, then had a cool-down phase with a lower learning rate and no weight decay for more fine-grained tuning. Then came phase 2, supervised fine-tuning, or SFT. Here, the model was trained specifically on high-quality datasets designed for instruction following and conversation, like WildChat and Slamorca. This is about aligning that raw knowledge with how humans actually expect an AI to behave, teaching it to follow instructions properly and chat coherently.
Right, so phase 1 is learn everything. Phase 2 is learn how to use it in a helpful, structured way.
Precisely. And the final step, phase 3, used direct preference optimization, or DPO. This is a really important human alignment technique. It further refines the model's conversational skills by training it to prefer responses that humans have ranked as better over responses ranked as worse. This helps ensure the model isn't just knowledgeable and helpful, but also safe, ethical, and generally an effective conversational agent. Each phase builds directly on the last one, making sure the final model is knowledgeable, capable, and aligned with human values and usefulness.
Wow. The theory and the training methods are incredibly impressive. It's a genuinely novel approach.
Mm.
But okay, the ultimate question always comes down to this. Do these models actually deliver on the promise? Let's look at the numbers. Does all this technical wizardry actually translate into real-world performance and that groundbreaking efficiency? Okay, prepare yourselves. Because when we actually look at the raw efficiency benchmarks, the numbers are, well, they're not just a little better, they're truly paradigm shifting. Let's compare this BitNet B1.582B4T model to some other well-known state-of-the-art models around the same size.
Indeed. Looking at the data, maybe the most striking thing, the most immediately impactful metric is the memory footprint. A 2 billion parameter BitNet model uses just 0.4 gigabytes for its non-embedding weights. That's tiny. Now compare that to, say, a LLM 3.21B model that needs 2.0 gigabytes, or mini CPM2B, which needs a whopping 4.8 gigabytes.
4.8 gigs versus 0.4.
Exactly. We're talking about a model that's anywhere from 3.5 to 12 times smaller than comparable full-precision models. This is revolutionary because it means it can genuinely run in places that were impossible before, like your average smartphone, maybe even embedded IoT devices. Think about it. A typical 7 billion parameter 16-bit model needs about 14 gigabytes of memory. That same model in 1.58-bit, probably around 0.8 gigabytes. This literally frees powerful AI from the cloud server and puts it right onto your device.
And the speed. This is incredible for user experience, right? We're seeing an inference latency of just 29 milliseconds on a standard CPU for that 2B BitNet model. Compare that to 124 milliseconds for mini CPM or 48 milliseconds for LLM 3.21B. That's a massive boost in responsiveness. It makes real-time applications like an on-device voice assistant feel practically instantaneous.
And the speed advantage scales up too. BitNet is reportedly 2.7 times faster than Llama at the 3 billion parameter scale, and an astonishing 4.1 times faster at the 70 billion parameter scale. This isn't just a bit faster. It's a total game changer for how interactive AI can feel. The energy savings are also critically important, especially as AI gets deployed more widely. The 2B BitNet model uses an incredibly low 0.028 joules for each inference task. This is roughly 6 to 23 times more energy efficient than other models in its class. Again, this isn't just incremental, it's a paradigm shift in resource use. It's essential for things like extending battery life on mobile devices and for promoting genuinely sustainable AI practices globally. It's a huge step towards greener computing.
Okay, so this data isn't just a collection of impressive numbers. It's real empirical proof that you can have extremely powerful AI running on your everyday devices using very little power, making it incredibly private and instant. But of course, the huge question that always comes up with this kind of efficiency is, does all that compression mean they're not as smart? Do we have to sacrifice intelligence to get these amazing efficiency benefits? And the answer, well, looking at these performance benchmarks, seems to be a pretty resounding no.
What's truly fascinating here, yeah, is that because of that careful quantization-aware training, BitNet B 1.58 performs competitively with, and often, surprisingly, better than full precision models of a similar size across a whole range of standard NLP benchmarks. Take common sense reasoning, for instance. On the Wino Grande benchmark, BitNet 2B scored almost 72%, 71.91. That significantly beats Alame 3.21B at 59.51% and Gemma 3.1B at 58.48%. That shows a really deep understanding of logical relationships.
That's a big jump in reasoning ability, which is often seen as a key sign of intelligence. But where it gets really interesting for me is on math and more complex reasoning. The BitNet 2B model got a remarkable 58.38% on GSM-8K. That's the benchmark testing grade school math word problems, the kind that need multiple steps of reasoning.
Right.
That score is actually higher than Quen 2.1.5B at 56.79% and way higher than Lamine 3.21B at 38.21%. This really suggests strong, complex reasoning skills. Even with those super low bit weights, this is where the smart really shows up.
It genuinely does. It strongly indicates that the model learned highly effective internal ways of representing information, despite having its bit width constrained so much. Now, there might be some areas for growth, sure, like the MMLU benchmark, which tests broad world knowledge. Quen 2.5, 1.5B slightly edges out BitNet there. But the overall average score across 16 diverse benchmarks for BitNet 2B is 54.19%. That's very competitive, with Quen 2.5, 1.5B at 55.23% and significantly better than Llama 3.21B, 44.90%, and Gemma 3.1B, 43.74%. This provides rigorous validation for the QAT approach. The model hasn't just survived the compression, it's thrived and learned to be highly effective within those tight constraints.
This means you simply don't have to choose between intelligence and efficiency anymore. You can actually have both, which fundamentally changes the trade-offs we've always had to make in AI development. And remember that crucial discussion we had earlier about post-training quantization versus quantization-aware training. This next set of comparisons really just hammers home why QAT is so incredibly important. It shows a really stark difference in the actual results.
It's direct empirical proof, yeah. Moving right from the theory to undeniable results. If you look at Quen 2.5, right, when you take the original full precision model and then quantize it after training down to 4 bits using standard methods like GPTQ or AWQ, you see a clear, consistent drop in performance compared to the original. For example, on that GSM-8K math benchmark, its score drops from almost 57%, 56.79 in full precision, down to around 50% for the 4-bit PTQ versions. That's a significant hit just from applying compression afterwards. But then you look at BitNet B 1.582B, it was natively trained using QAT. It operates with an even smaller memory footprint, 0.4 gigabit versus 0.7 gigabit for the 4-bit PTQ Quen, and it actually scores higher on GSM-8K at 58.38%.
Smaller and better on that reasoning and task.
Exactly. It's a powerful testament. And on another benchmark, IHEVL, which measures how well models follow complex instructions, BitNet 2B is about 5.5% better than the full precision Quen 2.1.5B and around 20% better than Quen's 4-bit PTQ versions.
So training it to be low bit from the very beginning isn't just a little better, it's dramatically better. It even allows it to surpass models that are trying to catch up by compressing after training. This totally validates that whole QAT philosophy.
Absolutely. This unequivocally shows that training a model with quantization awareness from day one is just the most effective strategy if you want highly compressed models that still retain state-of-the-art performance. And this then points towards a really significant, maybe even profound conclusion. BitNet seems to signal the emergence of a whole new, more efficient scaling law for large language models, one that completely challenges the conventional wisdom.
A new scaling law. What does that actually mean for how we build bigger, more powerful AI in the future? This sounds like a fundamental shift in strategy.
It is a fundamental shift, yeah. Traditionally, as you added more parameters to an LLM, the costs, memory, latency, energy, they just went up exponentially. It quickly became way too expensive to scale beyond a certain point. But with these 1-bit LLMs, the computational cost and the memory footprint of each individual parameter are drastically lower, like incredibly lower. This means that the performance capacity you might lose from the reduced precision, you can actually make up for it by just adding more parameters. Because the cost per parameter is so incredibly low now, we can afford to have many, many more of these super efficient parameters. The finding that a 3.9 billion parameter BitNet model can actually outperform a 3 billion parameter Llama model, even though the Llama model uses higher precision weights, that's a powerful demonstration of this new principle. It means we don't necessarily need individually smarter, higher precision parameters. We can potentially achieve even greater intelligence by having vastly more smart, super efficient parameters working together.
So instead of just making each parameter smarter by giving it more bits, you can just have way more incredibly smart, super efficient parameters that, as a group, achieve greater intelligence with less overall resource drain. That's a profound shift in how to build AI.
Exactly. It creates this completely different kind of trade-off that actually becomes more and more advantageous as you go to truly massive scales. This strongly suggests that the future isn't just about building bigger and bigger full precision models. It might actually be about building vastly larger yet profoundly more efficient one-bit architectures. This changes everything. It opens up a whole new world of possibilities for how and where AI can actually be deployed. Let's look at what that world might look like.
Okay, this is where the rubber really meets the road. It's not just theory anymore. This groundbreaking research is already being turned into practical tools. And Microsoft Research is definitely leading the charge here with some really important open source contributions.
Yeah, their commitment to open source, especially with BitNet.cpp, is absolutely crucial. This is their official C++ in frames framework, and it's highly optimized specifically for these one-bit LLMs. And notably, it's based on the very popular and super efficient llama.cpp project. That means it inherits this robust, community-tested foundation, which is great. The fact that BitNet.cpp exists means developers all over the world can start experimenting right now, building things, optimizing these models. It really lowers the barrier to entry. And it supports not just standard x86 and ARM CPUs, which is vital for mobile and edge devices, but they've also recently added GPU support, so it's becoming more versatile.
So the developer community can basically just grab these models, maybe fine-tune them for their specific needs, and start building incredibly efficient apps right on their own hardware without needing massive cloud setups. That sounds like true democratization of AI power.
Precisely.
Yeah.
And the immediate availability of pre-trained models on platforms like Hugging Face is a huge catalyst. You can find Microsoft BitNet B1.582B4T right there. They provide the packed 1.58-bit weights for inference, the BF16 master weights if you want to continue fine-tuning, and even versions in the GGUF format specifically for BitNet.cpp. This open access empowers this vast community of developers and researchers to start using state-of-the-art efficient AI without the massive cost of training from scratch. It just accelerates innovation everywhere.
Okay, this is where the really transformative impact of one-bit LLMs starts to become clear. Beyond the benchmarks and the tech specs, what does this actually mean for me, the listener, for the world?
It means personalized, really sophisticated AI that's always available right there with you without needing to constantly send your sensitive data off to the cloud. The primary, most transformative impact here is the potential to completely decouple powerful AI from the data center. By slashing the resource requirements, memory, computation, energy, these models can be deployed in places that were just totally inaccessible to large-scale AI before. Imagine your smartphone having a truly intelligent assistant, one that understands context deeply, responds instantly and critically, works entirely offline.
And the privacy angle on that is just huge. If the AI is running right there on your device, your data stays with you, always. No more sending personal questions or sensitive info to some remote server just to get an answer. It keeps your digital life actually personal.
Absolutely. And this extends way beyond phones. Think about smartwatches delivering genuinely intelligent insights, IoT devices becoming truly proactive and responsive, autonomous systems like drones and robots performing complex AI tasks reliably in real time without needing a constant internet connection. That's massive for robotics. And for consumer hardware like laptops and desktops. This means powerful AI tools become available to everyone, not just people with big cloud budgets. Multi-billion parameter models could run efficiently right on your everyday computer. It democratizes access, gets rid of the latency and the recurring costs you get with cloud APIs, and massively enhances privacy for a much, much broader audience. This isn't just about saving money for tech companies. It's about making advanced AI a genuinely personal tool that serves you privately and efficiently.
Okay, the potential is clearly immense, incredibly exciting. But, it's never quite a silver bullet, is it? There are always challenges, limitations that need to be tackled before one-bit LLMs are truly everywhere and fully living up to their potential.
Definitely. The biggest bottleneck right now, kind of ironically, is that our current hardware, especially general-purpose GPUs, is heavily optimized for doing high-precision floating point math. It's like having this amazing, super efficient new engine, but no car specifically built to take advantage of it.
Right.
Modern GPUs have these massive floating point units, wide processing pipelines, all designed for 32-bit or 16-bit numbers. While libraries like BitNet.cpp have done amazing work optimizing for CPUs, really unlocking the next level of efficiency will probably require purpose-built hardware. Things like ASICs, application-specific integrated circuits, or FPGAs, field programmable gate arrays, that are designed from the ground up specifically for these ultra-low-bit integer or ternary computations. This co-design of the software and the hardware is really crucial. And furthermore, while the performance is generally excellent across many, many tasks, there are still some specialized areas that demand extremely high numerical precision or really fine-grained nuance. Think about complex scientific simulations like modeling molecules or climate systems, or high-frequency financial trading.
Right.
These areas, even tiny rounding errors accumulated over long calculations, could lead to significant unacceptable results. For these niches, one-bit LLMs might still struggle a bit. Researchers are looking into things like adaptive precision, where maybe critical parts switch back to higher precision temporarily. And similarly, while they're good at many reasoning tasks, consistently matching the absolute best high-precision models for extremely long, complex chains of reasoning, that's still an active area of research.
It also sounds like while using a one-bit LLM is going to be incredibly cheap and accessible, creating a brand new one from scratch, really pushing the boundaries, that's still a pretty high barrier to entry, right? The initial training complexity and cost are still significant hurdles.
For now, yes, that's true. While inference is incredibly cheap, the process of training these models from scratch using quantization-aware training, it's still computationally intensive, it's still expensive. It requires significant expertise in these quantization techniques and access to pretty large-scale computing resources. That could limit the ability of smaller organizations or individual researchers to create truly novel foundational one-bit models from the ground up. However, the open source release of good pre-trained models significantly helps here because it allows fine-tuning without needing that massive initial training investment.
Okay, so with those challenges in mind, where are we headed next?
Right.
What's on the research frontier for one-bit LLMs? What new possibilities are opening up as these models keep evolving?
Oh, the future is incredibly exciting here. The most immediate and maybe most compelling direction is just scaling these models up even further. Researchers are working intensely on developing native one-bit architectures at the 7 billion, 13 billion, maybe even 70 billion parameter scales. Imagine a 70 billion parameter one-bit model running smoothly on your laptop or even a high-end phone. That will really test and validate these new scaling laws we talked about, proving that massive scale can be achieved efficiently. The idea of combining one bit with mixture of experts or MOE models is also incredibly promising. MOE models are already efficient because they only activate a small subset of their parameters for any given input. They're sparse in activations. A one-bit MOE model would be sparse in two ways. Its weights would be ternary, and its activations would be sparse.
Double sparsity.
Exactly. It's like having multiple highly specialized, super efficient mini-brains and only waking up the exact one you need for a specific task. The combined efficiency gains from that could be absolutely exponential, pushing the boundaries of what we even think is feasible.
And this idea you mentioned of hardware and software evolving together almost in lockstep, it really does sound like a whole new era for computing, not just for AI.
It feels like the natural and necessary next step. Research is continuing on optimizing hybrid architectures too, like BitNet A4.8, which uses 1.58-bit weights but pushes activation precision down even further to 4 bits, trying to find that perfect balance. But the most profound long-term path is definitely the coevolution of one-bit software and specialized hardware. If software like BitNet is proving what's possible, it creates this huge incentive for chip manufacturers to build hardware specifically designed for these low-bit operations. That virtuous cycle software innovation drives new hardware, which then enables even more efficient software that's likely to be the defining dynamic of the next era of AI development. This could fundamentally disrupt the current hardware landscape, which is so dominated by GPUs, and lead to a whole new generation of AI-optimized processors. The future of AI isn't just about the software, it's about completely reimagining the entire computing stack, right down from the algorithms to the silicon itself. Hashtag tag outro.
Wow, what an incredible journey through the world of one-bit LLMs. We've seen how that scaling dilemma of traditional full-precision models has been creating this critical bottleneck, massive computational, memory, financial, and environmental costs. And we've learned how model compression, specifically this quantization-aware training, seems to be providing a really radical, elegant solution.
We've really dug into the ingenious BitNet B1.58 architecture, its unique ternary weights, that Maddox 1 plus 1 trick, and those sophisticated training methods like the straight-through estimator and the dual-world approach that allow it to be both incredibly efficient and remarkably smart. The empirical evidence seems really clear. These models truly deliver, often outperforming bigger, higher precision models on key benchmarks while using just a tiny fraction of the resources.
The potential applications from
Yeah.
freeing powerful AI from those giant data centers to enabling truly smart private assistants right on your phone, they're just immense. And the future research promises even more breakthroughs, vastly larger models, maybe purpose-built specialized hardware that could completely reshape the AI landscape as we know it.
For you, the listener, this really points towards a future where advanced AI isn't just some distant, expensive cloud service that you have to send all your data to. Instead, it's becoming a personal, private, readily accessible tool. It's about AI becoming truly ubiquitous and sustainable, integrating seamlessly into your daily life without compromise, giving you access to powerful intelligence directly on your devices, enhancing your capabilities in ways we probably haven't even thought of yet.
Yeah, it's a future where you don't need a supercomputer or access to a massive data center to run a genuinely intelligent model.
Yeah.
Your everyday devices, your phone, your laptop, might just be powerful enough to handle sophisticated AI tasks locally, enhancing your privacy, giving you instant, seamless results. It's a profound shift in who gets access to this power.
So here's a final thought. Given that the BitNet team makes this bold claim, all large language models are in 1.58 bits. If the next generation of powerful AI truly does leverage this ultra-efficient paradigm, what new, maybe currently unimaginable applications will emerge when almost any device can host a sophisticated conversational agent completely offline? And what deeper questions will that raise about our reliance on centralized cloud infrastructure, both for global innovation and maybe even for individual autonomy?
That's a powerful thought to chew on, definitely. What does it truly mean when the power of AI moves out of the cloud and quite literally into the palm of your hand? This deep dive has certainly shown us the profound shift that seems to be underway. Thank you so much for joining us on this deep dive into the future of efficient AI. Keep questioning, keep learning, keep exploring.